Friends, welcome to my YouTube channel. Today I am going to discuss the composite bar problem, thermal stresses of the composite bar problem. So, before this video, composite bar, thermal stress composite bar, two cases will be there and two formula we derived already. What is? Stress load will be equal. Load will be the equal for stress steel and load will be equal to the copper. Both load will be equal. And another formula we got, strain will be equal for both cases. Elongations will be same for copper and steel. So we got this formula. So now little we'll discuss during the problem also. So this, what is the problem given? A steel rod of 20 mm dia passes centrally through a copper tube of 50 mm. External dia given, internal dia given for the copper. So steel dia is 20, internal dia of the copper 40 mm and external dia 50 mm. And they are asking both sides is fixed. Both sides are fixed. Then only thermal stresses will develop. If elongations will be freely, no stress will develop. Then what they are asking, if the temperature is assembly raised by temperature will change 50 degrees Celsius, how much elongations will come for the copper bar and how much elongations will for the steel bar, that they are asking. Young modulus and linear coefficient the given. Linear coefficient the given for the steel and copper both. Okay. So now first, if coefficient of linear expansions of the copper is here looks more, given more. Linear expansions of the copper is greater than the linear expansion of the steel. That means copper bar will elongate more. Copper bar will elongate more. So what is the here simple one concept there? Suppose two bar will be there, listen here. Copper and steel here there. So this will discuss now. Copper and steel. So if temperature will increase in the bar, what will happen? Both wants to elongate. Both wants to elongate. Both wants to elongate. But what is here? Linear expansions of the copper is more. So it elongate more and these elongations will be less. But due to this both end fixed, what will happen? This bar wants to elongate, but due to this they will push back. They will push back. So copper, for the copper, compressive stress will develop. But for steel, tensile stress will develop. For steel, tensile stress will develop because due to the less elongation. And this wants to reach up to this, but due to the less elongations, again they wants to come here. So this way, the tensile stress will develop. Okay, so this is the concept here. So elongation, copper bar having compressive stresses and steel bar having tensile stresses. Based on this concept, we are going to solve now. So first, what will be there? Two cases will be there. No? So area and all is there. So first find the area of the steel, pi by 4. What is it? 20 whole square. So 100 pi mm square will come. Then area of the copper, pi by 4, external dia 50 whole square minus 40 whole square. It will come 225 pi mm square. This will come 225 mm square. I think so. Okay. Now for equilibrium system. For equilibrium system, load will be the steel bar will be equal to the load of the copper bar. So load, so you can write tensile of the steel will be equal to, like this you write, tensile load of steel bar will be equal to tensile compressive load equal to compressive load of copper bar. This will be equal. So okay. So now we can write load. We know load is equal to stress into area. So we can write here load is there now. So we can write load of the steel, area of the steel equal to stress of the copper, area of the copper. So if we'll substitute value both area, so now see what will come here. Area of the copper by area of the steel into area stress of the copper. So if these two value, it will come, so it will coming stress equal to 2.25 stress of the copper. So one relations we know now. So one relations we got it here. Okay, now so elongations, now second case what is elongations of the both bar will be same. So delta L for steel will be delta L for copper. So elongation of the both bar will be equal. So now what we can write here? Elongation of the steel, because this thermal stresses problem. Thermal stresses along what will happen? Elongation of the steel equal to elongations of the, they will elongate mechanically and thermally. Mechanical elongation plus elongations of the thermal. Which one? Steel will be equal to elongations of the copper, mechanically elongate plus elongate of the thermal. So if one steps I am writing here, this is for copper. So this how this formula coming, that only I am writing here. So this mechanical elongations na PL by AE. So I will directly write PL by AE. Mechanically elongate, and thermal elongations will be there E. Thermal elongations will be there alpha. This formula already we derived. So E delta T into L. So this is the elongations for the mechanical elongation this and thermal elongation of this. You will substitute here. Both will write one step, then directly will write this formula. So what is there? PS or PS directly will write no P by A is equal to stress. Stress into L by E. We can write this. P by A is equal to stress. So what we will write directly here? Stress into L by ES plus linear expansions delta T into L for first. Second, what we will write here? E copper, the stress of the copper, E copper, this length plus linear expansions delta T into L. For this we wrote now. So now how to get this formula? I will write now here. See here. So this copper we have compressive stress, compressive, no? Copper have compressive. So load will be negative here. Load will be negative. So load by area stress. So this will be negative. Now if we'll take this side, what I wrote? Copper by EU. L will get cancelled. Both sides L will get cancelled. So if we'll solve this is the formula coming. This is the formula will come. Now if we'll substitute all the value here. See, stress, one steps I'll write, then I'll write the answer directly. Sigma Cu, as it is you write sigma Cu by ECU. This value will be there now. Newton meter if you write now 100 into 10 power 6. So 10 power 5 directly. How? See here 100 into 10 power 9. But this is the Newton meter square. 10 power 9. If you write mm square, 10 power 6 will multiply here. If you write here mm square, Newton mm square, so 10 power 6 will come. 10 power divided by 10 power 6. So it will come 10 power 6, 3 to the 5. So finally it will come 10 power 5 Newton mm square plus this will come steel. So 2.25 sigma Cu by 10 power 5. 10 to the power 5 is there na. 2 into 10 power, this is 2 into 10 power 5 for copper and 1 into 10 power 5 equal to delta T, they given how much? 50 degree rise is 50 degree, 50 and alpha Cu. How much? You take 10 power 6 here, common, then what will write here? 18 minus 12, 6. If we'll solve this, sigma Cu will come. If we'll solve this, sigma Cu will come. What value is coming sigma Cu? Just I will write here 14.117. 14.117 Newton per mm square. Newton per mm square. Now, if we'll substitute this value here, sigma S 2.2, so it is coming here, value is coming, sigma S coming value 31.76 Newton per mm square. So this answer stresses will be copper and stresses for the steel. These two will be the answer for this. So here what is your work? Main things will what will be there? Tensile load will be equal to the compressive load. So this is the formula. Now substitute all the value get the relation this. Now elongation of the steel will be elongation of the copper. So what is here? How we got this formula? How we got this formula? One previous video already we derived and got this, but I wrote little here. Delta S means this because thermal elongation. Thermal elongation na, it will be mechanical elongations plus thermal elongation. Again for this Cu, mechanical elongation and thermal elongation. Mechanical elongations what is? PL by AE, and thermal elongations will be alpha delta T into L. This if you will solve, this formula we are getting here. Once getting this formula, given data you substitute and you will get this answer. And now once you got stress of the copper, then substitute here stress of the copper, you will get this value. Okay, students, thank you.